Okay, cool. Well, it's my pleasure to introduce Louis Bédois from University of Sydney. He's a second-year PhD student working there with Peter Tuthill and Benjamin Pope as well from UQ. And so he's here today to talk to us about bulk of his PhD work on differentiable optics and his code, Deluxe.
Awesome.
Yeah.
Yes, I am. Yes, because I've got like the sharing the window, but it's full screen, so it cuts it out. Yeah.
So, and if anyone on Zoom, if the slides don't progress for you for some reason, just let us know and we will take care of it.
Wonderful, awesome. So thanks everyone, and especially thank you to Stephanie for inviting me. This is really exciting and you've been such a wonderful host. So yeah, as mentioned, I'm Louis. I'm working on differentiable optics as the bulk of my PhD. I've just started my second year and I've been developing a software called Deluxe that's designed specifically for this. And I'm really excited to talk about it today. So all of my slides are available online via that link, or you can use the QR code there if anyone wants to follow along. There's a lot of interactive videos, or you can go back and look at some of this stuff later. I've got a lot of links to tutorials and the documentation that a lot of this talk actually goes from. So if you want to look at some of that, please, I invite you to. And most of this work has been in collaboration with my supervisors, Ben Pope and Peter Tuthill, as well as a student, Jordan Dennis from UQ. All right. So what are the main problems that we're facing today in optics? There's a lot of different design and inference problems. So there's the James Webb, Tolman, which is a mission I'll talk to you a little bit about, and many other things that we can do as well. So as a lot of you will recognize, this is the James Webb Space Telescope primary mirror. And what this is actually looking at here is a phase map. So one of the big things that they need to do in order to align the segments is to be able to measure those phases on the individual mirrors so that they can make sure that you get a nice point spread function. And so as you can see on the right, we have a little sort of hot spot in one of the bottom right mirrors there. And that was actually caused by a micrometeoroid sort of hitting and degrading that mirror a little bit, which will continue to happen over time, which means that being able to measure the changes in the mirror is going to be really important to be able to continue getting really good science out of this telescope over its lifetime. And some people might also recognize this is the first transit curve that they released that has this very distinct little jump in it sort of halfway through. And so for those who don't know, this is actually caused by what they've deemed a tilt event, where there was some tension in the mirror. And what happened is as they were making the observation, it tilted, and that kind of threw some of the light out of where they were counting, because the way they measure these fluxes is they basically say all the light inside of these pixels, that's starlight, all the light outside isn't starlight. And so if you have a change in the way that your telescope is performing throughout that observation, then you get these false signals injected. So being able to understand and calibrate your system is a really important thing as well. So also the Tolman mission, this is one thing that they've been working on a lot. It is a mission we're trying to detect a habitable Earth-like exoplanet around the Alpha Centauri system by doing relative binary astrometry, which is we're expecting about a micro arcsecond signal, which would correspond to about 1 million times smaller than a single pixel on our detector, which is pretty ambitious. So we need to be able to understand the state of our telescope really well in order to be able to actually extract a signal of that size. And so there's a lot of cool design problems. So on the left, we've got one of what's called a diffractive pupil that generates our point spread functions like those on the right. So that's just sort of a little one of the design problems that this has been geared towards, as well as trying to calibrate it. So also there are a lot of other things we want to do. So for example, designing coronagraphs to be resistant to low wavefront error, designing anti-polarization coatings for things like the Subaru and Keck, because they're having issues where they're dealing with polarization effects as a function of elevation angle, because they're getting bouncing off different angles from their mirrors, which is causing some issues for them. And as a lot of people here work on is AO. And so even if you have a perfect wavefront sensor, because you have a non-common path from your wavefront sensor to your detector, you're always still going to have some other residual effects in there. That's another thing we want to look at tackling. And also in crowded fields where you have lots of stars close together, the conventional way of doing photometry, where you count flux inside a certain number of pixels, kind of fails if you have your stars that are really, really close together. And so there are a lot of other ways that you can approach that, differentiable optics being one of them. So also, your science goes here. We love to collaborate. We've built this really awesome platform. We're really excited about it. So if you work in anything like this, come and talk to me. We'd love to sort of develop out these capabilities with people. We've built this as a sort of open framework for everyone to come and work in. So yes, automatic differentiation optics. What does machine learning have to do with optics? Why are they related? What is differentiable optics? Well, let's start off by having a look at a neural network. Right, we all know this classic dense neural network structure. But what is that actually doing, right? It's taking some input vector on the left and it's mapping it to some output vector to the right in simple terms. And it's doing that via linear transforms and nonlinear matrix operations. All right, all good and well. So what about an optical system? What does an optical system do? Well, it maps an input wavefront to an output wavefront via linear transforms and nonlinear matrix operations. And so you might have noticed that these kind of look a bit similar in these representations. And really what that means is that an optical system is simply a constrained neural network. They're performing the same operations under the hood. And so an optical system is really a subset of a neural network that operates on a complex vector. And so that means that we can construct optical models, forwards models of optical systems inside of machine learning frameworks in order to take advantage of all these really, really powerful tools. I just want to emphasize here, I'm not talking about emulating an optical system with a neural network. I'm talking about creating a forwards model of an optical system within these machine learning frameworks in order to take advantage of automatic differentiation, because an optical system is just a subset of a neural network. So what is AutoDiff? Why is it useful? Well, it's not finite differencing, it's not symbolic differentiation, it's actually applying the chain rule to code and logic and maths. So it's done by the computer, and really there's one really powerful part of that, and it is that the computational time it takes to calculate those derivatives does not scale with the number of parameters that you're calculating those derivatives with respect to, which is super, super powerful. That's how they're able to build and train these million and billion parameter neural network models and actually feasibly optimize them in reasonable times. And so by building optical models inside of automatic differentiation frameworks, we can basically shed the whole curse of dimensionality. You can build much more complex and realistic forwards models and approach these problems in a much more simple and physics-informed way. And so, and also having the ability to have gradients go through your system, it gives you access to a whole host of other more really awesome optimization and inference algorithms. So let me tell you about my software, Deluxe. So we've built it to be fully open source. It's Python-based, built with JAX as our machine learning framework, which also means that it has a NumPy-like API. We've designed this to be as accessible to people as possible and as flexible as possible so that everyone can sort of do the various different things you do in optics. We'd love to collaborate with people because I've pretty much spent the last 2.5 years of my science taking optical modeling software and then shoehorning AutoDiff into places where it doesn't belong. And it's very painful and you can do a lot of great stuff, but it was just slow and difficult to use. And we sort of finally found the right sort of set of packages and have built this framework. And in the last 6 months, I've designed and built this software and pretty much done my entire last 2.5 years of science as well. So that's part of why I'm so excited, is I know that there's so much more that everyone could be doing. And I think it's crazy that we're not taking advantage of the fact that, you know, optical systems and neural networks are structurally isomorphic. Everyone should be doing this. So just a few hot button points. Obviously, AutoDiff, as I've mentioned, is really kind of the key part. Also, because we're using JAX, it has just-in-time compilation, which means you can write all of your code in Python, run it once, and then they will compile that into XLA code, which means it'll run a hell of a lot faster. So you don't have to worry about your Python for loops anymore. And Google pays engineers a hell of a lot of money to make this XLA run really optimized on a whole host of GPUs, GPU arrays, TPUs, and CPUs. And they've even shown, I believe, that for matrix multiplication, I think it is, that the JAX optimized XLA code runs as fast on GPUs as Fortran, which is pretty hardcore. So yeah, and so we've found some great packages that means that the software is object oriented. And on top of that, it means that we naturally integrate with some really great optimization libraries like Opdax, which is the library that is built and maintained and used by the Google DeepMind team. They do some pretty great stuff. And similarly, I've also just recently got the my software to plug into NumPyro, which is a probabilistic programming language, which now means that we can do MCMC algorithms through these big complex models, and we have access to a whole host of other HMC algorithms that take advantage of these derivatives to do really, really awesome stuff. So let's look at some of the problems. So yeah, there's a link here to the tutorial. This is one of our documentation tutorials that basically covers this stuff. The Tolleman mission, one of the key parts is to design this diffractive pupil. So the key point is that it's a binary pupil. I won't go into too much detail about it, but that's sort of one question. If you have a binary pupil that can only have two values, how do you get gradients through that? Because you need, it needs to be continuous in order to have gradients. And so we designed this cool little algorithm called Continuous Latent Image Mask Binarization, or CLIMB, because astronomers love a good acronym. And what that is you take a nice set of pretty continuous basis vectors like this, and you combine them together in order to get a singular, continuously changing underlying basis. And what you do is you essentially threshold that and say anything above this value is a 1, anything below this value is a 0, and you use an oversampled basis. And what you do is you fit a slope in those boundary regions. You fit a plane to that so that you actually have continuous behavior across that. So what we have here is our underlying continuous basis on the left. We have our binary pupil in the middle, and then we have our point spread function on the right. And I will show you now because I like having pretty videos. And it's just a lot of fun to watch. And so that's sort of how, some of the ways you can do get continuous gradients through more complicated systems. So don't freak out. There's only 2 slides with maths, and it's not that important. The whole point here is that for Tolleman, we needed to consider a few different factors, and mainly we wanted to be able to constrain the binary separation because we're performing relative binary astrometry. We're trying to measure planetary signal that's tugging on these 2 stars. And because our signal is so small, we need to be able to understand the state of our telescope at any moment, because defocus drifts will dwarf our signal by orders of magnitude. So what you can do is you can just construct really complex arbitrary loss functions and then let JAX do all the hard work and calculate your gradients for you, and design a whole bunch of pupils. And because you can also build a whole because you're in these machine learning frameworks, you can batch them together. So this is only 9, but I think when I was actually running this on my laptop CPU, I was doing 80 at the same time. But I'll just show you now because it looks really cool. I like making pretty pictures. That's most of this presentation, don't worry. Only 2 slides of math and we're already through one of them. You can just see they all go and sort of end up with these really distinct, similar features, which is super fantastic. So what about some other problems? So optical design is another one. So again, we have a tutorial in our documentation here that covers a lot of this information. And so let's say we have a diffractive pupil that we've designed, and we have our PSS on the bottom there, and then we have a regular unobstructed airy disk-like system on the right. And we want to see how well they'll perform in a realistic system, right? So we want to know how the different parameters such as defocus and all that relate to our binary separation, which is our scientific signal we care about. So math slide number 2, what you can do is calculate essentially what is the Cramer-Rao lower bound, which is just the minimum variance of your parameter in the best case. And the reason I sort of put this up here is because what you're looking at in the bottom there is that's the covariance matrix, which is defined as the Hessian of your log likelihood. And so we have our 2 little nabblers there. But the thing is, because we've built this in an AutoDiff framework, that means that we can let them do the hard work for us. So it's not even just, first order derivatives, but you can calculate Jacobians and Hessians arbitrarily through these systems with respect to arbitrary parameters. And once you have your covariance matrix, that then means you can plot your posteriors and visually examine how your parameters relate to each other. So here is just a reduced example of the optimized pupil that we made as compared to the airy disk one. And so as you can see, the binary separation, which is this parameter we care the most about, our optimized pupil massively outperforms the binary star, the airy disk system, because it suffers from less covariance with other parameters that we care about. So you can directly understand the relationship between these parameters really, really easily. And the question is, what if we wanted to go further, right? You have your covariance matrix. What if you then calculated the entropy of that? And then what if you wrapped that whole calculation inside another gradient? And so now you can actually optimize your system, your optical system, or any number of parameters in it with respect to any number of observables that you want to do. And so you can really crank up the number of parameters because you don't have scaling with complexity. So this is just the summary statistics of the posteriors on the bottom. The blue one is before optimization and the bottom one is after optimization. As you can see, all of the posterior constraints get tighter after optimization, and you start with the pupil like at the top and you end up with one at the bottom. As you can see, you can sort of come up with these really awesome pupils and do these really sort of first principled optimizations that is quite trivial. And yeah, I think it says 1 minute on my laptop or something like that on CPU. And you can just add more and more parameters if you want. It just doesn't quite matter. So instead, I've got another little demonstration link. It's not quite a tutorial yet. I've only just got this jigged together, but it is pretty cool and I would like to show you. So yeah, if you have some data and you want to understand, what's actually happening in your system, what does a physicist do? Well, they run an MCMC on it because that's our Swiss Army knife of, you want to understand something, you MCMC it. So, but because we have an AutoDiff based system, that means we actually have access to even better MCMC algorithms that are known as Hamiltonian Monte Carlos that again allow you to build much more complex systems and understand more and more parameters and not suffer from this scaling issue. So this is just a little test case that I made where you're looking at a binary star with some optical aberrations, and you want to constrain all of your binary star parameters as well as the background noise in your image and the optical aberrations. And so don't freak out too much. You're not actually meant to really see anything. The whole point here is that you can understand really, really complex relationships all the way from your astrophysical to your optical to your instrumentation parameters and see exactly how they relate to each other. And you can sample through them. And the point of showing that there's all of these different posteriors here is that I think it's 12 parameters. I think this took 7 minutes to run on my laptop CPU, and it took 7 minutes to run with one parameter as well. You can just scale these up and understand whatever you'd like about them. And so it's super, super powerful. All right, again, another tutorial link if you'd like to take a look. What if you want to calibrate your system? You've got some unknown thing going on. You need to know how your telescope is bending, what's happening on your detector. So how do you do that? So we have a Tolman-like system here where we're taking 4 images of a bunch of different stars through a diffractive pupil. And the thing is, we know approximately where our stars are and how bright they are, either through Gaia data, or you can do some deconvolutions to get sort of rough initial guesses. But we're going to say we have no idea how our telescope is bending or warping, and we have no idea about the individual pixel sensitivity. So this is the key thing here. We're applying a flat field to this data and trying to recover that, because it's kind of just, there's a hell of a lot of parameters, and it's a problem that before you've had to do in K2, all of these really crazy decorrelations between astrophysical signals and instrumental signals and different observation patterns and all that. And this is kind of the point of AutoDiff, is with these constraints removed, you don't have to do any of that anymore. You can just directly learn these parameters. So what we're going to do is we're going to run gradient descent on our stellar positions and fluxes, our optical aberrations, and our interpixel sensitivities. So it's about 65,000 parameters. And you can bump that up. I think I did up to like 1,000 by 1,000. and it doesn't really take that much longer. But yeah, so I think this overall took about 5 minutes to run on my laptop CPU. All of this has just been done without any actual specialized hardware, no GPU time. It all just basically runs really, really trivially. So I'll show you each of these individually. Why is that already loaded? Yeah, so because there's a lot of parameters that we're learning, I'll have to sort of show them being learned one at a time. So the astrophysical parameters here, we're looking at the individual position residuals over the training, and then the fluxes over here. And then these are just the image residuals as they go. And so I'll just let that play here. And as you can see, we learn exactly what's happening astrophysically, and our residuals go and disappear. And once we get to the end there, we are just down at the photon noise level. So we've extracted all the information that is actually there within our system. And so let that run one more time. All right, so what about our optical aberrations? So these are preloaded. Yes, so as I said, we're starting from a naive perspective. We don't know what's actually happening within our optical system, and we want to understand the warps and bends. And so what you're seeing here, this is the root mean squared optical path different residual. These are our Zernike coefficient values. And this is what the actual true optical path difference that we're trying to recover is. This is what it is at the current state, and this is what the residual is. So I'll just let this play. As you can see, we get some nice little oscillating around, and we're just able to find the solution quite trivially. I'll let it go one more time, just because it's fun to watch. As I said, lots of pretty videos and only 2 slides of maths. And then we'll go through the next one, which again is preloaded. So this is the one that really has the meat of all the parameters. This is the individual pixel sensitivity. So there's 65,000 parameters that we're learning here. This is the overall mean sensitivity residual. And so you'll see this goes and hits a noise floor eventually because we have detector and photon noise. And as I said, we're extracting all the information that is there. So this is the best one to watch, in my opinion. It's just a correlation plot of the true sensitivity values versus the recovered sensitivity values. So as we'll see as we learn it, these will go and fall along the y equals x line because they've recovered their true values. And then, yeah, this is what we're actually looking for. This is what the current state of it is, and this will be the residual. So now I'm just let that play. And so you can see our 65,000 pixel parameters go and all just line nice and beautifully along our y equals x line, showing that they've been recovered correctly. So future work, what are we looking to do beyond this? Well, there's a whole bunch of different things. Really, as I've said, we've designed this to be more of a framework. So we know that there's so much that can be done. We're working with some people at Arizona, potentially going and building in some ray tracing modules to be able to do different bulk optic design. We've got some really great free space propagator algorithms in the pipeline at the moment to be able to do holographic phase mask design. Also, there's a lot of interesting work going on in photonics. So that link there is to the Google X team is basically building a differentiable optical framework for photonics specifically in JAX. So they think it's a good idea. We've thought about putting in some of some modules in as well and building that in to be able to integrate with a lot more of the photonic work that's going on now, because that's being integrated with the rest of astrophysics. And the non-common path error, as I mentioned at the start, which I know a lot of people here are working on as well. We think, you know, if you implement an actual physical forwards model inside the real-time loop, then you can start to correct for this non-common path error, as well as learn the state of the system at the same time. And as I said, we're really looking forward to collaborating with people. So whatever else you think might be useful, please come and talk to me about what your work is. I'd love to hear it. I think there's a lot of exciting potential for things going on here. And of course, I encourage you to go and have a play with the code. It's all available on my GitHub there. We've got tutorials we're building out, and we're hoping for the 1.0 release in about 2 months. But yeah, so thank you very much. If you have any questions, I'd love to take them.
Do you want to come up here just so they can hear you online? They're broken. Yeah, they don't function anymore.
So in terms of optimizing the optical design,
Mhm.
have you figured out a way to feed in the signal to noise ratio of your detectors into that optimization, like for your phase mask?
Yeah. So because you sort of build this full end-to-end optimization, you can directly feed in, for example, like photon noise and background noise and variances as well into those in order to sort of maximize your extractable signal. Given, if you have a fixed telescope hardware, then there's only certain things you can design. But yeah, so you can basically, if you can model it, then you can feed that in and have that as a part of your actual design loop. So you can just build these really complex systems and keep optimizing them further.
Nice.
Cheers.
Any other questions? Jane, do you wanna? Sorry. No.
Okay, so for someone new coming into it who's never used this before, but I guess has maybe undergraduate level, I guess, optics experience, how long would it take them to, for example, set up a system and then go from there?
Well, I think it kind of depends on what you want to do. There's definitely a degree of optical knowledge that you sort of need to sort of get going, but we've built out a lot of tutorials that are designed to try and sort of show you all the different things that you can do. And I've, as I said, a lot of my work is over the past couple of years have been taking other people's optical modeling software and like really shoehorning in AutoDiff and like understanding it from a deep level. So I've had a lot of experience working with other softwares, and I think a lot of them have some issues in sort of how easy they are to get going with them. And so that's been a big focus of what I've been doing, is sort of trying to not make the mistakes I think that those softwares have made. So I think, I'm obviously a bit biased because I built it, but I think it's the easiest framework to work in. And a few other people that I've sort of gone and talked to and have interacted with it sort of have found it to be quite easy to do and use. So I think, depending on what you want, if you just want to set up a basic optical system, it'll take, there's a little tutorial that'll take 2 minutes. If you want to build a full forwards model of an adaptive optics system, well, we haven't built in the adaptive optics system things yet. So, it's part of why we're looking to collaborate with people, is I don't have the expertise of how to model those certain things, but we know that it's absolutely something that can be done and could be super valuable. So it depends on what you want to do, but I think it's a really simple system because I've worked with so many different optical modeling softwares over the years and sort of tried to bring the good bits without bringing the bad bits as well.
Yeah, that's good to hear. But yeah, it might be worth, I don't know, maybe just trialing it with some of the undergrads around.
Yeah.
Sydney and stuff to see if, because after you've been in this for a while, right?
Yeah. I'm like, it's hard to gauge. It's hard to gauge. Yeah. And as part of why we focus a lot on sort of building out these tutorials, sort of like help people get off the ground with it. Because there was a while where trying to work with new software can be quite intimidating sometimes. And so yeah, we've also sort of taken a bit of the mantra of sort of not doing magic stuff under the hood, kind of being sort of clear and explicit about what's happening, so that you can sort of learn a lot more along the way as you sort of build those different things. So, but yeah, that's a great idea.
Thanks.
Cheers.
So actually, can I ask a follow-up question?
Yeah.
So if you had to compare learning Deluxe to learning ZMAX and trying to construct an optical system, and then whether it's ray tracing or free form, and then trying to optimize said system, how would you compare the two, the learning curve for the two?
Yeah, well, for most people I've spoken to who work with ZMAX, like I have as well, ZMAX is super difficult to work with and super finicky software. So there's definitely a much bigger learning curve with ZMAX, and there is a bit of nuance in that sort of ZMAX is implementing a much more a physical model. You can do thermal modeling and stuff like that it's more fleshed out. But in terms of just going and setting up and getting a PSF out of an optical system, you know, it could take you days with Zemax just to kind of get started, because you've got to know so much about the wider system. But we've sort of broken the system down into its sort of like fundamental operations and sort of set up, you know, a little tutorial showing like how to put these together. So for most basic optics stuff, there are tutorials that you can just go and straight grab the code off. So I think it's, you know, much quicker. And then in terms of optimization as well, sort of another point is as I was saying before, about the sort of the no magic as we don't like, because in Zemax you just say cool, optimize, and then you wait, and then it sort of gives you a thing, and it's like, there you go, and it's like, oh, okay, cool, what happened, what's going on here? But yeah, we're not doing that. So, you know, and we've integrated with optimization libraries like Opdax that allow you to really easily pass in your system and really like finally control what it is that you're doing and understand what you're doing quite simply. So yeah, and that's one of the main things that one of the packages, Equinox, that we've used, that allows you to do object-oriented JAX. It lets you take derivatives rather than with respect to a vector that you have to play around with. You actually pass in your whole optical model object to your loss function, and then can arbitrarily take derivatives in higher order gradients through that. And so it's been one of the most powerful things, is that if you want to switch what you're doing, you just basically change one line for your loss function. So I want to take my grades with respect to this instead, and rather than have to change and chop and change different parameters where they're getting passed through and all that. So yeah, I think I've learned a lot along the way and tried to implement as much of that as possible to make it useful.
Any other audience questions in the house? I have one more. So it may be a naive question, but how easy is it to physically construct the optimized pupil that you found, say, for the Alpha Cen telescope? That's sort of really complex.
You mean like the actual making of it in the real world? Or? Yeah. So that's actually the reason we need to be binary is because we're actually putting a little small ripple across the edge of it, so that you can get these little spectra in the corner, so you can calibrate the effective temperature of the star. So actually it's actually not hard to design these binary pupils, because they're macroscopic, and so they can just go and use lithography to cut those out. But there are limitations, for example, in the cadence of that grading that you put over the top of it, that's to do with the right head of your of your lithography device and all that. So the actual fabrication of the bulk design is not so hard, but there are certain constraints on the fine structure. And actually, some of the Google X Photonics teams, they've designed some really cool sort of algorithms that actually allow you to input the information about the right heads of your lithography device in order to design these photonic components. That's cool. I would encourage you to go check out that link and look at what they're doing, because there's some other really cool things where they're doing sort of binary design with some cool methods to get continuous behavior through it. So yeah.
All right, thank you.
Awesome.
Do you have questions online from anyone?